Hello everyone and welcome to this example. The example reads, water flows through a pipe at the rate of 30 liter per second. The absolute pressure at point A is 200 kilopascal. So I can just note that down. Pressure at A, PA, is 200 kilopascal. And the point B is 8 meters higher than point A, as we can spot in here. The lower section of the pipe has a diameter of 16 centimeter. We can note that down as well. The diameter in here is 16 centimeter. And the upper section narrows to a diameter of 10 centimeter. So the diameter in here is 10 centimeter. Part A of the question asks us to work out the velocity of the stream at point A and point B. So we need to work out what is VA and we need to work out what is velocity at B in here. And the second part of the question wants us to work out the pressure head at point B. So I'm just going to label that to be PB for the moment. Now, before we start solving this question, I need to consider a reference point for height, like a datum line. And I'm going to consider that point to be right here. So height at this point, I will be considering that to be 0, and height at that point will be 8 meters. So I'm going to label that as well in the figure. Right over here, it is 0 meter. And right on top in here, we have 8 meter. So 8 meter is our HB and 0 meter is our HA. Right, I think I've labeled everything in this figure, and now let's get to working out. Now we know that the flow in this water is a streamline flow because all questions that we are dealing in here are streamline flow. And we know the formula for flow rate as well. Flow rate equals velocity times area. In the question as such, we assume that the mass flow rate at the inlet is same as the mass flow rate at the outlet. So we can write that to be QA equals QB, where Q represents the mass flow rate. And that is equal to VA times AA, and that is equal to VB times area of cross-section B. Okay, so the mass flow rate in here, which is represented by VA times AA, is equal to the mass flow rate right over here at the outlet, which is VB times AB. And another equation that we will be using to solve this question will be the Bernoullis theorem. I'm going to note that down in here as well. Bernoullis theorem. And Bernoullis theorem states that pressure at any point in this pipe is going to be a constant. So if you're considering pressure at this point, all dynamic, kinetic, and absolute, all pressure at this point is equivalent to the pressure at that point. So we can write the Bernoullis equation to be pressure plus half rho v square plus rho gh is equal to a constant. Now, the next step is to pick all our units and make sure they are in standard form so that as we keep working out, we are consistent with our units. Otherwise, there's a chance that we could get things wrong. Now, the first thing is the flow rate. The flow rate, which is Q, is 30 liter per second. And I'm going to change that into meter cube per second. So divide it by 1,000 and you get 0.03 meter cube per second. Okay. Second, we need to look into the diameter. The diameter at A is 16 centimeter, and we can write that to be 0.16 meter. The diameter at B is 10 centimeter, and I can write that to be 0.10 meter. Right, the first part of the question wants me to work out what is velocity at A and what is velocity at B. In order to work that out, I can use this mass flow rate equation that I've written down in here, as mass flow rate is going to be constant throughout the system. And in order to work that out, we need to work out what is area at A and what is area at B. So cross-sectional area over here and cross-sectional area over there. So area of cross-section A can be found by just using pi r square, which is equal to pi times, we know the diameter divided by 2 will give us the radius, so the whole square, and working that out will give us our answer to be 0.0201 meter square. And same way we can work out area of cross-section B, again using the same formula pi r square, which will be pi times 0.10, which is the diameter at B, divided by 2, which will give us the radius square, and working that out will give us 0.00785 meter square. So now we know what is the cross-sectional area at A, and we know what is the cross-sectional area at B, and we also know the mass flow rate in meter cube per second. Okay, now let's get into solving the first part of the question, where it asks us to find the velocity of the stream at point A and point B. So from here we know that this is our mass flow rate. And in here we know what is the area of cross-section A, and this is the area of cross-section B. All right, now let's input these values into the mass flow rate equation and work out what the velocity will be. So velocity at VA is just going to be mass flow rate at A equals velocity at A times cross-sectional area of A. We know that the mass flow rate is 0.03 equals VA, which is a velocity which we need to find, times the area, which is 0.0201. So VA equals 0.03 divided by 0.0201, which will give us the velocity to be 1.49 meter per second. Okay, second, we can work out what is velocity at VB, and to work that out we can use the mass flow rate equation at B. QB equals velocity at B times cross-sectional area at B. We know that the mass flow rate is going to be constant, so 0.03 equals VB times the cross-sectional area is 0.00785. Hence VB is going to be 0.03 divided by 0.00785, and that will give us the velocity at B to be 3.82 meter per second. So we can see that at the inlet the velocity is lower, and as it proceeds ahead the velocity increases. And it does make sense, because we did learn that when there is a streamline flow through a pipe, at narrower regions, the velocity increases. So when the surface area decreases, the velocity of the fluid flowing increases. Okay, now let's get into the second part of the question, which wants us to work out the pressure at point B. The Bernoullis theorem states that the average of all pressures experienced at the inlet is equal to the average of all pressures at the outlet or anywhere throughout the system. So Bernoullis theorem, if you apply this theorem, it stays constant at any point in the system. So we can say that the Bernoullis theorem, or the average pressures at this point, is equal to the average pressures at that point. So we are going to work out pressure at point A and point B. We can write the Bernoullis theorem as PA plus half rho VA square plus rho GH1, because we are referring to location A, point A at the moment, is equal to pressure at B plus half rho VB square plus rho GH2. Now, to make the working out easier, I'm going to list out all of these values just at the bottom. Okay guys, I've rearranged this a bit. I've got the diagram in here. I've got pressure at A, which is 200 kilopascal, velocity at A, 1.49 meter per second, velocity at B, 3.82 meter per second, height over here 0 meter and height in here, which is 8 meter. Now the missing variable that we need to find is the PB. So I can just rearrange this entire equation to make PB the subject. PB equals PA plus half rho VA square plus rho GH1 minus half VB square minus rho GH. Now we can just substitute in the values. So PB will be pressure at A, which is 200,000, plus half times density of water is 1,000, times velocity at A is 1.49 square, plus density of water again 1,000 times G 9.81 times H1, which is 0. So that section will be 0, minus half times VB is 3.82 square, minus rho, which is 1,000 times 9.81 times H2, which is 8 meter. Just plug this into your calculator. You don't need to plug this in because you know if you times it by 0, you're just going to end up with a 0. Input all of these values into your calculator and you will work out PB to be 115,334 pascals or 115 kilopascal. Now remember, you are not done yet because the question wants you to work out the pressure head at B. Pressure head is going to be a value in meters. Now we know that pressure equals rho GH. We need to work out what this H will be. We know the pressure. It is 115,334 equals density of water, which is 1,000 times 9.81 times H. And working out H will give us 11.75 meters. And that is the pressure head. I hope you understood this question well.